Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 7. In this lecture, I am going to discuss thermal conductivity of metals by applying Drude'S theory. Okay, so let's get started. Before begin with Drude'S theory, let me just give you some basics which is required for this. We know very well, naturally heat transfer occurs from hot end to cold end. Okay, hot end to cold end. This is what we observe naturally. Clear? Then I have told you in metals heat transfers occur due to lattice vibration, heat transfer occurs due to movement of free electrons. Okay, so in metals heat transfer occurs due to lattice vibration or due to movement of free electrons. Okay, the heat capacity the thermal conductivity due to movement of free electrons, I am going to represent this by the symbol K electronic. This is electronic contribution to thermal conductivity, and I am going to represent this by the symbol K lattice. Right? Drude introduced this model. Okay, actually when Drude introduced this model, he did not know much about the lattice vibrations. Okay, because Drude introduced this model just after the discovery of electron by J.J. Thomson. So at the time, Drude thought that the thermal conductivity of metal is due to the movement of free electrons. So we are going to focus on the thermal conductivity due to the movement of free electrons. Free electrons are also called conduction electrons. Okay, then what is the definition for thermal conductivity? Thermal conductivity, how to define this, is denoted by the symbol K. Thermal conductivity in general is defined as minus heat flux occurs at a given location divided by the temperature gradient near that location. Okay, what is the heat flux occur at a given location divided by temperature gradient near that location, and minus sign, you know very well, in the last lecture I told you what is the reason for the minus sign. Clear? This is the formula for thermal conductivity. And you also know that last class I have told you that J is nothing but heat flux. You can calculate J by using the formula number of conduction electrons that is actually moving, or number of free electrons into what is the average velocity of the electron, average velocity with which the electron is moving, into what is the energy possessed by the electron, energy. Okay, if you multiply these three, you will get what is called the heat flux. Okay, yeah. So based on these ideas, we are going to move further in this. And remember, in metals the free electrons are moving randomly. Okay, what is the difference between free electrons under electric field, free electrons due to temperature difference? Listen, under electric field the free electrons move in one direction, whereas because of temperature difference, if heat transfer occurs from hot end to cold end, we cannot say that electrons move always from hot end to cold end. No, electrons electron motion is completely random. Okay, thermal motion is completely random. So electron can move from cold end to hot end as well as from hot end to cold end. Okay, so this is the point you should keep in mind. So free electrons move randomly. Free electrons move randomly. It's a random motion. Okay, free electrons move randomly. Clear? This is another important point you should keep in mind. Okay, since they move randomly, right, we have to define an average velocity of the electron. Let the average velocity of the electron be v, right, and the square of the average velocity of the electron, I'll represent this as v square, average of the square velocity. Then another term called tau. What is tau? It is the mean time between two successive collision. Mean time between two successive collision. It is also called as relaxation time. Relaxation time. Okay, yeah. Then another important point I like to give here. See, since heat transfer occurs from hot end to cold end, okay, temperature near hot end will be high and temperature near cold end will be low. So temperature is a function of the position of the position. Okay, yeah, I'll explain this as we go along. Okay, now we are going to see the derivation of electronic contribution to heat capacity, electronic contribution to thermal conductivity using Drude's theory. Okay, yeah. For this, what I'm going to do, consider a one-dimensional metallic crystal. Okay, consider a one-dimensional metallic crystal. So let me take a one-dimensional metallic crystal like this. As in that, this is a metallic metallic piece, and it is one-dimensional in nature. Okay, let us take this axis as x-axis. Okay, and let us assume this end as hot end and this end as cold end. So heat transfer occur naturally from hot end to cold end. Okay, remember, okay, I'll take some point, some reference point here, say x. Okay, I am going to focus, right, what is the heat flux that is occurring, net heat flux that is occurring at the point x, because you know very well free electrons move from hot end to cold end. Free electrons can also move from cold end to hot end. Okay, therefore heat transfer occur not only from hot end to cold end, heat transfer also occur from cold end to hot end, but the net heat transfer, that is what we are going to focus. Net heat transfer occurs from hot end to cold end. Clear? So what I'm going to do here, see, suppose if you take any point near hot end, temperature will be high here. Any point at cold end, if you take, the temperature will be low here. So temperature is a function of the position x, right? Not only that, energy of the electron, you know very well, the free electrons in metals, according to Drude theory, the free electrons are assumed as it is something assumed like ideal gas. Okay, something assumed like ideal gas in a container. Okay, ideal gas obey kinetic theory equation, according to which the energy depends only on temperature. So the free electron, the energy of the free electron depends on temperature. Temperature depends on position. Therefore I can say that energy depends on temperature, energy of the free electron depends on temperature, and temperature depends on position. So this is the usual way of representing energy of a free electron. Clear? Then now what I'm going to do, so this is the approach given by Drude. What is the energy of the free electron? How many free electron having some energy, okay, moving from hot end and crossing the point X. Then how many free electrons having some energy moving from cold end to the hot end and crossing the X. Okay, this is what we are going to focus. So you know very well, collision, if collision occurs, energy will change. So we need to identify, okay, the location, the average location where the collision would have occurred before the point X. Okay, so what I'm going to do, let me write the next page. See, so this is the one-dimensional solid we have assumed. Okay, and let us take some point X here, and this is the hot end and this is the cold end. Okay, now what I'm going to do, from hot end to cold end, free electrons are moving. From cold end to hot end also free electrons are moving. But when free electrons move from here, it will undergo many collisions. Similarly, when free electrons move from hot end to cold end, yes, it will undergo many collisions. Collisions changes the energy of the electron. Okay, but what we are going to focus is, what is the energy of the electron that is coming to the point X. So for that, I need to find out where the last collision would have occurred before the point X. Okay, so for that, what I'm going to do, the average velocity, let the average velocity of electron, free electron, average velocity of free electron, let it be Vx. Okay, this symbol, this bracket symbol indicate average. Vx is the velocity because we have taken one-dimensional crystal, one-dimensional metal, so we have taken only Vx here. Okay, but for simplicity, I am going to represent this simply as Vx. So if I write Vx, right, keep this in mind, Vx means average velocity. Okay, so you know very well average velocity. What is velocity? Distance by time. Okay, so Vx equal to distance by, let me take the distance as d1, distance by time taken. If I take time as tau, what is tau? It is the mean time collision, mean time between two successive collisions, right? So when time become tau, definitely one collision will occur, right? So before this point X, where would the last collision occur? Okay, so last collision that would have occurred, before X, from hot end to cold end. I'll just put like this, HC, hot to cold. From hot end to cold end, if free electrons are moving from hot end to cold end, before the point X, where would be the last collision occur? Okay, let me represent that distance as d1. Okay, d1 equal to, right, is nothing but Vx into tau. Vx into tau. So from X, I'll subtract this Vx into tau, right? So I'll take some distance d1 here. From distance d1 from X, at distance d1, the last collision would have occurred. Okay, so let me take this point as X minus Vx into tau. So last collision that would have occurred before X from hot end to cold end is this is actually d1, but this is actually where the last collision would occur, X minus d1, correct, which is nothing but X minus Vx into tau. Exactly at this location last collision would have occurred, right? So after this point, the electrons moving, free electron moving towards X, assume that the electrons do not undergo any collision. After this point, the electrons which are moving towards X, they do not undergo any collision. Just assume like that. Okay, on average, right? Therefore, the energy possessed by the electron at this point is carried by these electron and moving towards X. Clear? Yeah. Similarly, where would be the last collision occurred? From X, okay, in the from cold end. Okay, right, because you know free electrons are also moving from cold end to hot end. So if free electrons move from cold end to hot end, it will undergo many collisions, right? Before x, where would be the on average where would be the last collision occurred, right? Let me take that distance as d2. So we need to find out what is this point. Let us assume this is the point where last collision would have occurred for free electrons that are moving from cold end to hot end. Clear? So last collision that would have occurred before x from cold to hot, from cold end to hot end. Let me represent that point as x plus d2, because x increases from left to right. So carefully, x value increases from left to right. So this point is supposed to be x minus something, x minus d1, and this point is supposed to be x plus d2. So it is x plus d2. What is x? Sorry, what is d2? d2 is nothing but vx into tau. We have to use the same formula because average velocity remains same. So vx equal to d2 by tau, or d2 equal to vx into tau. So this is the position, that is x plus vx into tau. This is the position where last collision would have occurred for the free electrons that are moving from cold end to hot end. Okay, after this position, assume that there is no collision occur. So the free electrons that are moving towards x have energy, okay, whatever energy they possess at this point. Clear? Okay, this is very important point. Keep this in mind. Now what I'm going to do, listen. So what is the heat flux? What is the heat flux, right, from hot end to cold end? Let me represent simply this as JHC. Heat flux from hot end to cold end at the point x, right? To find heat flux, you must know how many free electrons are moving towards x, okay, and what is the average velocity of the electron, and you must also know what is the energy of the electron. Listen carefully. Now from hot end to cold end, I am going to consider free electrons that are moving from this point, because before this point many collisions would have occurred, so energy of the electron keep on changing. After this point, on average there is no collision occur, so free electrons move freely and pass through the point x. Okay, what is the energy possessed by these electrons? Energy depends on position. So at this position, whatever energy exists, that is the energy carried by those electrons. Now we need to identify what is the number of free electrons that is moving towards x from this point. Okay, you know very well, NF is the number of free electrons per unit volume. Okay, NF, wherever you take, wherever position you take, number of free electron per unit volume is same. Okay, so at this location, let us assume the number of free electron per unit volume is NF. And I have told you in the beginning that under as a thermal motion is completely random. So the free electrons, okay, move from this position towards hot end, or it can move towards cold end. So free electrons can move anywhere, but since it is a one-dimensional solid, it can move either in the either towards hot end or towards cold end. That's the only two possibilities exist. Okay, that's the two possibilities exist here. Now let us assume 50% of the electron, right, out of NF electrons, 50% of the electron move towards x. Therefore NF by 2, 50% of the electron moving towards x, into average velocity of the electron. Let me represent average velocity as Vx, I have told you already, into what is the energy carried by each of these electrons. What is the energy carried by the free electrons that is moving from this position towards x? It is nothing but the energy at this point. Okay, so you know very well, energy depends on temperature, and temperature depends on position. What is the position? X minus Vx into tau. right? So at this position, whatever energy the free electron possesses, those free energies are those electrons, okay, that is the energy carried by the free electrons towards X. Okay, so this is the heat flux occurred from hot end to cold end. Clear? Then what is the heat flux that occur? Because electron motion is completely random, so electron not only move from hot end to cold end, electrons also move from cold end to hot end. So what is the heat flux from cold end to hot end, right? So that is, we have to consider this point now. From this point, assume that there is no collision. On average, there is no collision occur, okay, between X and X plus Vx tau. So whatever electrons that are moving towards X, right, from this point, they carry energy, that is energy possessed by the free electron at this point. I'll repeat, the free electrons moving towards X carry some energy. What is the energy carried by the electron? It is the energy possessed by the free electron at this point. Clear? And we have enough free electrons here also. Okay, enough is nothing but number of free electron per unit volume, which is same everywhere, right? So number of free electron present per unit volume, right, here is enough. Let us assume that half of the electron moving towards X. Therefore number of free electrons moving towards X from cold end to hot end is also NF by 2 into average velocity of the electron Vx into energy possessed by the each electron. Okay, what is the energy possessed by each electron? Which is T into T of X plus Vx into tau. Because energy depends on temperature, temperature depends on the position. Clear? So this is the heat flux from hot end to cold end, and this is the heat flux from cold end to hot end. Now we need to identify what is the net heat flux. Net heat flux is equal to heat flux from hot end to cold end minus heat flux from cold end to hot end, because naturally we know that heat transfer occur from hot end to cold end. So we have to subtract this from this. Clear? Now, so I am going to subtract this minus this. Okay, I am going to subtract this from this. So here NF by 2 Vx, NF by 2 Vx is common, so I'll take these two as common term. NF by 2 into Vx is, I will take this as a common term, into, I'll put a bracket like this, into energy possessed by the electron at this location X minus Vx into tau minus energy possessed by the electron at the location X plus Vx into tau. Clear? We should close the bracket. Now, what is the energy possessed by the electron at this location? Listen, this is very important. Energy energy possessed by the electron at this location E, Tx minus Vx into tau. Okay, which is actually very close to the point X. Therefore we can say approximately that the energy possessed by the electron at this location is approximately equal to energy possessed by the electron at the position X, okay, minus Vx into tau into the first derivative dE by dx. Okay, if you include second derivative, third derivative and higher derivative terms, yes, you will get almost very good energy, but it was said that if you take first derivative itself, okay, up to first derivative itself will give you very good result. So you need not worry about the second derivative until, because the second derivative, the other higher power derivatives contributions are negligible. Clear? Then what is the energy possessed by the electron at this location? X plus Vx into tau. This is also approximately equal to energy possessed by the free electron at the location X plus Vx into tau into dE by dx. Okay, now I'm going to substitute these two here and I'm going to subtract. So what we'll get is, let me write in the next page. Yeah, see this. So J net heat transfer equal to NF by 2, okay, and Vx is already there, into in the place of this I'll put this one, energy at the location x minus Vx into tau into dE by dx. Okay, then we have to subtract this. Okay, I'm going to, in the place of this term, I'm going to put this one, but we have minus here, therefore this will become minus, this also become minus. So I'll write once, energy at the location x minus Vx into tau into dE by dx. Clear? Now what I'm going to do, I'll cancel these two. This is positive term, negative term, and these two are one and the same, so let me cancel it. And here we have minus Vx into tau dE by dx. Here also I'm having minus Vx into tau dE by dx. So if I add these two, I'll get minus 2 times Vx into tau into dE by dx. So what we get is NF by 2 into Vx into, if I add these two, I'll get minus 2 into Vx into tau dE by dx. Clear? We can cancel this 2 and this 2. So what we get is minus NF into Vx become Vx square. Okay, remember this Vx square, right, is actually average velocity, okay, square of the average velocity of the electron. This Vx square actually means square of the average velocity of the electron. Okay, right now this is the meaning, right, into tau into dE by dx. Clear? This is the net heat flux that occurred at the position x. Now let me make some more things here, some more changes here. Minus NF into Vx square into tau into, I'll write this dE by dx as dE by dt into dt by dx. If I write like this, nothing going to change, because if I cancel dt dt, I'll get this, I'll get the same expression, right? Yeah. Now, so this is the net heat transfer that occurred at the position x. Okay, listen carefully. This is for one dimension, right? So in 3 dimension, let me write here. Real crystals, real metallic crystals are 3 dimensional, right? So in 3 dimension, right, we have to convert this velocity into 3 dimensional, right? So how to do that? Listen, in 3 dimension, okay, before going to that, let me give this point. This is very important. See, I have told you Vx square is actually square of the average velocity of the electron. Clear? But what Drude assumed is that he assumed that this is equal to, right, it is not actually equal, Drude assumption, it is approximately equal to square of the average of the square velocity. Actually it is square of the average velocity, but Drude assumed that is this as average of the square velocity. Clear? Yeah, this is actually yeah, approximately they are equal, right, but not actually. Now we also know that in 3 dimension, the square of the average of the square velocity along x plus average of the square velocity in y direction plus average of the square velocity z, x component, y component, z component, if you add all these 3, you will get the average of the square of the net velocity. Clear? And here we also know that since the free electrons are independent, they are moving in randomly in all direction, therefore we can also say that in this case average of Vx square equal to average of Vy square equal to average of V square z. These are all equal. Okay, since these are equal, in the place of v square y I can put vx square. In the place of v square z also I can put vx square. So I'll get vx square plus vx square plus vx square. So 3 times vx square I'll get. Okay, let me write in the next page. So 3 times average of the square velocity, x component of square velocity, equal to average of the square velocity. We get an expression like this. Then what is vx square? Equal to 1 by 3 times average of the square velocity. Right, so this is the expression for vx square. Now I'll put this expression in the net heat flux expression. So J net equal to what is the net heat transfer minus NF. I'll keep all the term as such, minus NF into, in the place of Vx square I'll put this one, 1 by 3 times average of the square velocity into tau into dE by dt into dt by dx. Clear? Okay, then let me make some more thing here. You know very well the free electrons. Okay, the free electrons can move randomly throughout the metallic crystal, and these free electrons, they possess only translational kinetic energy. Potential energy of the electron inside the metal is assumed as 0. I have told you already. Potential energy of the free electrons inside the metal is assumed to be 0. Therefore, the only energy possessed by the free electron is the translational kinetic energy. Clear? And you know very well, translational kinetic energy E is equal to, right? Since the free electrons obey classical mechanics, right? The free electrons are treated as classical particles, right? We can apply equipartition theorem, right? According to which the energy of each degree of freedom is given by the formula of kBT, right? Translation, listen, free electrons can move in all direction. Therefore, each free electron possess 3 translational degrees of freedom. Therefore, the energy is 3 into half kBT. Right? If I differentiate this with respect to temperature, dE by dt equal to, I'll get 3 by 2 into kB. What is this? This is nothing but, let me write this as CV electronic. I'll put small c here. This represents the heat or heat capacity per electron. Okay, it is nothing but heat capacity per free electron for one free electron. Okay, which is nothing but 3 by 2 kB. So keep this in point in mind, very, very important. So dE by dt is nothing but CVE. But what our focus is that what is the heat capacity for NF electrons? For one electron, this is the heat capacity. For NF electron, we have to multiply this by NF. Therefore, if I multiply both sides by NF, what we'll get is NF into dE by dt. Okay, I am going to multiply both sides by NF. Why we are multiplying? Because dE by dt will give you heat capacity per free electron. What we want is heat capacity for NF electron. What is NF? Number of free electron per unit volume. Clear? So how to get the value? NF into dE by dt. Multiply this side also by NF into small CVE. Okay, this I am going to write as capital CV electronic. This is nothing but electronic contribution to heat capacity. Clear? Substitute this value in this equation. So I am going to replace this NF and dE by dt. Okay, replace these two and put this one. So what we'll get is J net heat transfer equal to minus 1 by 3 into average of the net square velocity into relaxation time tau, okay, into CV electronic into dt by dx. This is the expression for net heat flux occur at the point x. Clear? Due to the temperature gradient dt by dx. Okay, then now, so what is the heat capacity? So therefore, electronic contribution to heat capacity, electronic contribution to thermal conductivity is given as, you know very well this formula, J net heat transfer divided by the temperature gradient dt by dx. Okay, and we know the expression for J net. Okay, this is the expression for J net. Okay, substitute this value here. So here we have a dt by dx. In the denominator also we have dt by dx. So those two cancel. So what we get is electronic contribution to thermal conductivity is equal to, okay, let me write once. I'll keep this dt by dx as such. In the place of J net, I'll put this value. What is J net? Minus 1 by 3 into average of the square velocity into tau into CV electronic contribution to heat capacity for n of electrons into dt by dx. Okay, this is J net. dt by dx cancel each other. Minus into minus become plus. So electronic contribution to heat capacity is equal to not heat capacity, I'm sorry, thermal conductivity, right? What is this? This is nothing but electronic contribution to thermal conductivity. K represents thermal conductivity. So what is the electronic contribution to thermal conductivity? Is nothing but 1 by 3 into average of the square velocity into tau into CV electronic. Okay, yes, this is the expression for thermal conductivity of metal by the Drude'S equation, right? This is the Drude'S equation for thermal conductivity of metals. Okay, so Drude obtained this value experimentally. Drude calculated these values, right? Drude calculated these values through kinetic theory equation. Okay, and he substituted those values and he calculated the electronic contribution to heat capacity, the electronic contribution to thermal conductivity, and this value agrees with the experimental value, almost close to the experimental value. Okay, yeah, so the calculated value of thermal conductivity and the experimental values are very close. So Drude theory could explain the electrical conductivity of metal as well as thermal conductivity of metal, okay, in a nice manner. Clear? What we are going to do in the next class is that what are the success of this model and what are the limitations, right? This is what we are going to do in the next class. I hope you have understood this concept clearly. Okay, I stop here. We'll continue in the next class. Thank you for listening.